Welcome to the lecture series on electromagnetic field theory. This is lecture number 3, constitutive relationship. So in this lecture we are going to cover these many topics. The first topic is capacitivity or permittivity of the medium and inductivity and permeability of the medium. Next is instantaneous constitutive relationship for linear matter in general sense and in simple sense. Next will be complex constitutive relationship for linear matter in general sense and in simple sense. Then comes admittivity and impedivity of the medium. After that we will see characteristics of matter, linear and simple matter, free space, air or vacuum, diamagnetic, paramagnetic and ferromagnetic material, and finally non-magnetic material. And at the last we will see AC capacitivity or inductivity, dielectric or magnetic loss factor, dielectric or magnetic loss angle, and loss tangent. So when I say constitutive relationship, one thing comes in the mind, that the relationship is very simple. And yes, it is simple, but it is simple when the matter is linear as well as we call it in simple sense. In that case, we have a relationship between the field quantities and the material properties, and that particular relationship looks very simple. But in general sense, when we say that in general sense, the relationship is not so simple, it is a complex relationship. So I am going to break that myth that the constitutive relationships are simple. Yes, of course it is simple, but for a very special case, and we are going to see that. So let's start this lecture. So before starting the lecture, I am going to give you overview of what we are going to see in this entire lecture. So when I say constitutive relationship for linear matter in general sense, the equations looks something like this. We already know the equation of this form, that D is equal to epsilon E, B is equal to mu H, and J is equal to sigma E. These are the equations which we are already familiar with. But they are correct only when the matter is linear and we are calling it in simple sense. We are going to see that why we call it simple sense and why we call it general sense. Now here these quantities, field quantities E, D, B and J, they are written in scripted form, that is scripted letters are used, E, H, J, they are written in scripted form. That is why we call it instantaneous field quantities. This has already been covered in lecture 1 in detail. And when the field quantities are complex, then we replace these scripted letters with Roman letter E, H, J, B and D, etc. Okay, so these two sets of equation is instantaneous field quantities for linear matter in general sense and in simple sense. And these two set of equations, they are written in complex field quantities for linear matter in general sense and in simple sense. So in this lecture, this is the basic overview which we are going to see. Apart from this, yes, of course, admittivity and impedivity is covered, and the characteristics of the medium in for linear matter, for free space, and for non-magnetic and as well as magnetic materials are also covered. Other than that, we are also going to see how the epsilon and mu can be written in a rectangular form and in polar form, and we can derive the loss tangent with those equations. Alright, let's start now. So the first topic is capacitivity, permittivity or inductivity and permeability of medium. So epsilon is called the capacitivity or permittivity of the medium. Mu is called inductivity or permeability of the medium. For free space, this epsilon becomes epsilon naught and mu becomes mu naught. Okay, and there is a relationship between epsilon and epsilon naught as well as mu and mu naught, and that relationship is epsilon is equals to epsilon r epsilon naught and mu is equals to mu r mu naught, where this epsilon r and mu r is called relative permeability and relative permittivity of the medium. So epsilon r is relative permittivity and mu r is relative permeability of the medium. Alright, so what are the values of these epsilon naught and mu naught? The value of epsilon naught is 1 over 36 pi into 10 to the power minus 9 farad per meter, and mu naught, its value is 4 pi into 10 to the power minus 7 Henry per meter. So that is why you can see that why they are also called capacitivity and inductivity of the medium, because the units of epsilon naught is in farad per meter. So it represents capacitivity of the medium, as well as the unit of mu naught is Henry per meter. That is why we are calling it inductivity of the medium. So you should know these two names. The more popular name is permittivity and permeability, but you should also know that they are also called capacitivity and inductivity of the medium. Alright. Now next is instantaneous constitutive relationship for linear matter in general sense and in simple sense. Now we have already seen that in a general sense the constitutive relationship looks something like this, where D is the field quantity and epsilon is the material property. Now why is this complex relationship coming here? Usually in an atomic particle which is made up of matter has mass. So atomic particle has some mass as well as it has charge q, mass m and charge q. Okay, so when the field changes rapidly, field when I say E or H, when it changes rapidly, then these particles cannot follow the field so quickly. For example, suppose an electron has been accelerated by the field and the direction of E changes, then there will be a time lag before the electron can change the direction because of its momentum, because it has mass. Okay, suppose we have an electric field in this direction and we have an electron over here. Suddenly, so since the electron is over here, the electron is also moving in this direction, and suddenly the direction of electric field changes in this direction. So because there is a mass of this electron, so it will take some time for this electron to move in this direction. Such a picture holds for J because it has free electrons. It will also hold for D when the electron is a bound electron. And a similar picture holds for B, except that the magnetic moment of the electron is the contributing quantity. So now you have understood why these time derivatives of electric field, time derivative of magnetic field, they constitute towards the relationship between the field quantities and the material properties in a general sense. Okay, so whenever these time derivatives, first order time derivative, second order time derivative, and all other higher order derivatives, when they are negligible, when it is 0, then we can say that the constitutive relationship is D is equal to epsilon E, B is equal to mu H, and J is equal to sigma E. Now the most important thing is that why are the derivative terms important? Because these derivative terms, they will contribute to the impedivity and admittivity of material in the time harmonic case. Since we are studying electromagnetic field theory, where there is a particular frequency associated with it, so that is why we are calling it time harmonic case. We are not dealing with a static case where your omega is 0. No, our omega is not 0. It can be as high as of the order of 10 to the power 9 or 10 to the power 12. 10 to the power 9 is gigahertz range, and 10 to the power 12 is terahertz range. Okay, so in that case, these time derivatives and all other higher order time derivatives, they contribute to the impedivity and admittivity of material. Okay, that is why these time derivative terms are important. Okay, so now before going into these two topics, let us quickly see how complex constitutive relationship for linear matter in general sense and in simple sense looks like. So I have taken this particular equation. I have chosen this particular equation where this electric field E has been taken out common. So this E has been taken out outside this bracket. Now when we change from instantaneous field to complex field, we know that the scripted letter E is changed to the Roman letter E. So that is what we have done here. And these time derivatives, they can be written as j omega. Okay, so let me change the color. So this d by dt became j omega, and d2 over dt square is j omega whole square, which is minus omega square. So that is what is written over here. Okay, all right, let me clear this out so that you can see it clearly. Okay, now this entire term, this should be epsilon 1 j omega, and this should be plus, this is del t square epsilon 2 minus omega square. This should be minus omega square. All right, so now this entire term inside the bracket, this is a complex function of omega, and we give it another name. We call it epsilon cap. So this entire thing inside this bracket is written as epsilon cap, and it is a complex function of omega, and its value, its expression is epsilon plus j omega epsilon 1 minus omega square epsilon 2 plus all other higher order terms of omega. So this particular equation becomes d is equal to epsilon cap E, and this is valid for media which is linear in general sense. So you understand that? So when the medium is linear in general sense, we will use epsilon cap. Whereas when the medium is linear in simple sense, we will simply use epsilon. Why? Because when omega term goes to 0, tends to 0, then these epsilon cap, mu cap and sigma cap, they can be simply written as epsilon, mu and sigma. So for linear matter in simple sense, it becomes d is equal to epsilon e, b is equal to mu h and j is equal to sigma e. Whereas in general sense, d is equals to epsilon cap omega, b is equals to mu cap omega and j is equal to sigma cap omega, where these epsilon cap, mu cap and sigma cap are given by these relationships. Alright, okay. Now let's start with this topic, admittivity and impedivity of the medium. Now we already know that J is sigma E plus J omega epsilon E. But now we understand that for a linear matter in general sense, this sigma and this epsilon should be replaced with sigma cap omega and epsilon cap omega. So that is why I have written sigma cap and epsilon cap here. Now if you take this electric field E outside the bracket, we are left out with this term, and this entire term inside bracket is denoted as y cap omega, and y cap omega is called the admittivity of the medium. Similarly, the magnetic current M is j omega mu h. We have replaced mu with mu cap, so the expression becomes M is equal to z cap omega, where z cap is j omega mu cap and z cap is called the impedivity of the medium. Now I am writing this expression one more time here. So y cap is equals to sigma cap plus j omega epsilon and z cap is j omega mu cap, where this epsilon cap, mu cap and sigma cap is given by these relationships. Okay, all right. Now let's start with the characteristics of matter. In this topic we will see matter which is linear and simple, free space, air or vacuum, they are all the same, just with different names, diamagnetic, paramagnetic and ferromagnetic material and non-magnetic material. So these equations I am writing it again over here for our reference. Okay. Now for free space, sigma cap becomes 0, epsilon cap becomes epsilon and mu cap becomes mu naught. Epsilon cap becomes epsilon naught. Okay, so when we substitute these values over here, we get the admittivity for free space as y cap is equals to j omega epsilon naught and z cap is equal to j omega mu naught. Okay, now since you already know that epsilon is equal to epsilon r epsilon naught, which simply tells us that epsilon r, the relative permittivity, should be equal to 1 for free space. What happens for non-magnetic metal? For non-magnetic metal, sigma cap is equals to sigma, epsilon cap is equals to epsilon naught and mu cap is equals to mu naught. So when you substitute these values, you get the admittivity of non-magnetic metal as sigma plus j omega epsilon naught and impedivity of non-magnetic metal as j omega mu naught. For non-magnetic dielectric, what we will get? For non-magnetic dielectric, the sigma cap is 0, epsilon cap remains epsilon cap and mu cap becomes mu naught, that is free space permeability. So the admittivity and impedivity expressions becomes like this. For ferromagnetic material, Now, before looking at into the ferromagnetic material, we must also know that diamagnetic material mu is less than mu naught, and for paramagnetic material mu is greater than mu naught. But for ferromagnetic material, mu is very much large than mu naught, and it becomes, the relationship is non-linear. So for diamagnetic and paramagnetic material, mu can be approximated with the free space permeability, that is mu naught. But for ferromagnetic material, we cannot do that. So for ferromagnetic material, sigma cap is sigma, epsilon cap remains epsilon cap, and mu cap also remains mu cap. So the admittivity and impedivity relationship becomes like this. Alright, so I hope you have understood how the complex permittivity and complex permeability, these values epsilon cap, mu cap and sigma cap, they are complex permittivity and complex permeability of the medium, and this sigma cap is complex what do we call sigma? It is conductivity, complex conductivity of the medium. Okay, all right. Now let's look at this topic. AC capacitivity or inductivity, dielectric or magnetic loss factor, dielectric or magnetic loss angle, and loss tangent. We have already seen that this epsilon cap, which is a function of omega, is a complex quantity. So a complex quantity can be represented in the form of rectangular form, that is A plus minus JB. Okay, so similarly it has been written over here, that is epsilon prime minus J epsilon double prime. This is complex permittivity written in rectangular form, and it can also be written in polar form, where this is the magnitude part of the complex permittivity and this is the phase part of the complex permittivity, where this epsilon cap is called the AC capacitivity and epsilon double prime is called the dielectric loss factor, and delta, this particular delta, is called dielectric loss angle, and delta is given by the expression tan inverse imaginary by real, that is tan inverse epsilon double prime divided by epsilon single prime. And when we take the tangent of this angle delta, we call it loss tangent. Okay, so for dielectric material, this is good for dielectric material. What if the material is magnetic? If it is a magnetic core, magnetic material, in that case our complex permeability mu cap is also a complex quantity, and it can be represented in terms of rectangular form, that where mu prime is AC inductivity and mu double prime is magnetic loss factor. And in the polar form, it can be written as mu cap magnitude times the phase part e to the power minus j delta m, where delta m is magnetic loss angle, and it is written for as an expression as delta m is equals to tan inverse mu double prime divided by mu prime. And if you take the tangent of this angle delta m, you call it a loss tangent. Okay, all right. So I hope you have understood this lecture. At the last, I have one question for you, which is a question of gate level question. The question says, consider a non-magnetic dielectric. The permittivity of the material is plotted as a function of frequency as shown in figure below. So if you see in this figure, here epsilon prime divided by epsilon naught, that is normalized epsilon prime with respect to the free space permeability has been plotted here. Similarly, normalized epsilon double prime is also plotted as a function of frequency. It has been asked that to determine, you have to determine epsilon cap, that is complex permittivity of the medium at 0.1 gigahertz and determine the loss tangent. The second question is determine impedivity of the medium and comment on its behavior. Okay, so let's see how we can solve this. So it can be easily solved. It's a very simple question. You have already seen the expressions. The first question says determine the complex permittivity of the medium. So epsilon cap omega, we know that epsilon prime minus j epsilon double prime. So the value of epsilon prime and epsilon double prime, this we have to find it out. So epsilon prime over epsilon double prime is for 0.1 gigahertz. So 10 to the power 9 is 1 gigahertz. 10 to the power 8, this is 0.1 gigahertz. So at this point the value of epsilon prime is 3. So 3 minus j epsilon double prime. So this is 0.1 gigahertz. The value of epsilon double prime is 0.02. Okay, and the loss tangent tan delta is equals to epsilon double prime over epsilon prime, which is equals to 0.02 over 3, which is equal to 6.67 into 10 raised to minus 3. This is unitless. This is the loss tangent, and this is the value of complex permittivity of the medium. The second part of the question is to determine the impedivity of the medium and comment on its behavior. So the impedivity is z cap omega, which is equals to j omega mu cap, which is a function of omega. So now, since in the question it has been given that consider a non-magnetic dielectric. So for non-magnetic material, this mu cap is simply mu naught. So you can write j into omega, that is 0.1 gigahertz, that is 2 pi into 10 to the power 2 pi f 10 to the power 8 into mu naught is 4 pi into 10 to the power minus 7. So if you solve it, you will get j 8 pi square into 10, that is j 80 pi square. Since it is plus j, so it has been also asked to comment on the behavior. So the behavior of the medium is capacitive. So it is capacitive behavior. Okay, so we have substituted 2 pi f, which is omega, and this value of mu naught is 4 pi into 10 to the power minus 7. So it simply becomes j 80 pi square. So that's the value of impedivity of the medium. Okay, so I hope you have understood this lecture. So this lecture basically talks about the constitutive relationship, and the important part in this lecture is that the constitutive relationship can be written in form of general sense and simple sense. and this relationship in general sense turns out to be admittivity and impedivity of the medium, which gives us the relationship for the magnetic loss factor, dielectric magnetic loss factor, AC capacitivity and inductivity, and the loss tangent. So I hope this lecture was helpful for you, and if you have any doubts, please write it in the comment box. Thank you.